So, welcome for the final time to NP live lessons. So, this is the final lesson for the final exam, Physics Paper 2. So, this is your final push. Now, this comes quite late. This was meant to be done before half term, but here we are. So, there are a few topics to go over tonight, which is a Unit 5, Forces, Unit 6, Waves, and Unit 7, Magnetism. And for those taking triple science, the space topics will be embedded in others. Now, we'll just wait a few more minutes before we start. Hmm. Okay, let's start. We'll start off with Unit 5, Forces. So we've got to start from the basics first. You may be asked in the exam to define a few things. For example, what's meant by a scalar or a vector quantity, and a contact force and a non-contact force. I'd like to give two examples of each as well. So you can take some notes on whatever you'd like, let's say your book, notes electronically, or just even paper itself. So to define each of them, a scalar quantity will just have magnitude or size only. Whereas a vector has a magnitude and a direction. So two examples for each could be, for scalar ones, it could just be distance or even speed. Whereas vectors, it could be, for example, forces or even velocity. Now, as the name suggests, a contact force needs something to be in contact for it to happen. These would be common push and pull forces. This could be, for example, friction, thrust, and so on. Whereas non-contact forces don't need two things to be in contact. These tend to be field kind of things, for example, electrostatic forces of attraction. These could also be magnetic ones. Now take these notes down and then I'll move on to gravity. Next, we have gravity here. So this is another example of a non-contact pulling force. So for example, large objects like the Earth cause gravity to act on us and they pull us inwards. Gravity can also be called weight. Now, there's a formula for this which will be given in the exam as either weight is mass times the gravitational field strength or W equals mg. It's nice knowing this year that you don't have to memorize these formulas. Now we're going to label this formula with the units for each. So forces, like weight or gravity, are always measured in newtons. Mass is measured in kilograms. Gravitational field strength is measured in newtons per kilogram. You'll be often given this in the exam, the gravitational field strength. On Earth, it's about 9.8 newtons per kilogram. So, for example, for every kilogram you weigh, gravity will act 9.8 newtons of force on you. Now, the difference between weight and mass is that mass really doesn't change much. It's mass is the amount of stuff on you or inside you, whereas weight is the actual gravity. This can actually change depending where you are, for example, on the moon, on the planets, and so on. Now, gravity can find its way into things called force diagrams. So this is where we draw an object and see all the forces that interact on it. Now, if there are multiple forces on our diagram, how do we know what's happening overall? For example, let's say we have a car that has an engine and it produces a thrusting force going forward of about 750 newtons, and it goes against resistive forces that add up to 200 newtons. And we're going to draw something called a free body diagram. Now, usually you'd have a scaled like arrows. For example, 1 centimeter is, let's say, 100 newtons, but in this case it doesn't matter much. We're more on the maths for this. So we'll have our car is a dot, the objects you're interested in is the dot, and you'll have all your forces pointing from the dot to wherever in any direction, and they'll be drawn as arrows. For example, this is our thrust force, and this would be 750 newtons. And this needs to be a little shorter, the resistive forces, which are about 200 newtons. Now, since they act against each other, you'll have to take them away. So overall, the rightwards force is larger, so the overall force would be to the right. And we do 750 minus 200, and we just get 550. So our resultant force is 550 newtons. And just remember to put the direction to the right. Now for higher tier, you'll need to know how to resolve some forces. Now let's say we have two forces that act at right angles to each other, so they're not as nice as last time. For example, we have a force acting 5 newtons downwards and then 6 newtons to the right. So two separate forces. Again, let's draw a free body diagram to show this. So I have my object, this will have the 5 newtons downwards, and then the 6 newtons to the right. Now, how do we this time find the overall resultant force? Now, that's what we call resolving forces, finding the resultant force. Now, usually you do this on some squared paper, and you draw the forces tip to tail. So we start with one of the forces, let's say the 5 newtons down, and then we'll draw the next force after it, the 6 newtons to the right. And what you get is this little triangle. So our resultant force generally will go in this direction. Now, if you're drawing this on some lines on squared paper, don't forget to use a scale. For example, 1 newton every 2 centimeters, something like that. So when you measure your resultant force, you can use your ruler and use your scale to make an accurate guess, perhaps. Or if you're confident enough, you could use some maths. For example, you could use Pythagoras, and to find the angle as well, you could use trigonometry. So here, as a warning, you would probably need a protractor. In this case, I'm going to do the maths method, which is going to be a bit more accurate. So overall, the resultant force, its magnitude or size, would be this squared plus this squared, and we take the square root. This gets us the root of 61, so we get about 7.81 newtons. And I've given that to three significant figures. Now, to find the angle, you could do whatever you want. You can find whatever angle, but it usually needs to be from the vertical or from the horizontal. For example, I'm going to find this one here, the horizontal angle. To do that, we have our opposite and our adjacent. And our angle is 39.8 degrees. Now, if you use a protractor, the mark scheme will allow a little tolerance of about 2 or 3 degrees above or below this. So don't worry if you've got like a really accurate one like this. Next, we can look at forces and life cycles of a star. So this is for triple science students only. So this links well to what we've just seen so far with the forces. So we see that the force, the stars will often begin as a nebula. So this is a cloud of hydrogen gas. It might have a bit of helium inside there. Then, due to gravity, this nebula will come closer together. All the gases will just compress together, and this forms a protostar. Now, as they come together, their temperature will raise and go higher, and this can cause nuclear fusion to happen. So this is where lighter elements like hydrogen will then fuse with other hydrogen atoms to form heavier elements like helium. Now, if the temperature and pressure is high enough, a star in its main sequence is formed. Now, what we have is the star's core. That's where most of the fusion takes place. And then its outer layer, like this. Now, what happens is, if I draw the forces in blue, you will have gravity acting inwards due to its own weight. However, there is lots of energy released due to nuclear fusion, so it's balanced. Now, at this point, when the star is in its main sequence stage, its forces are in equilibrium, and it's stable. That's until the hydrogen runs out, and depending on the size of the star, a few things could happen. So stars that have a similar size to our Sun will eventually stop fusing for a bit, and the core is crushed due to gravity. So if I write diagram 1, this is still triple content only. So we have our core. Now the hydrogen runs out and the fusion stops, so there's nothing to act against the gravity. So that core is just compressed by gravity. However, like before, the gravity can also cause it to increase in temperature, and so more fusion can actually happen. So where, for example, helium nuclei can start to fuse. Now this extra energy causes the star to swell and get bigger into a red giant. Now eventually, some of these heavy elements can't be fused, they won't release enough energy, and the outer layers of the star is shed, and that leaves the core, known as a white dwarf. Now, for stars that are much larger than our Sun, this is what they often ask in exams, a similar thing happens. So the fusion stops for a bit if they run out of hydrogen, then the core gets crushed, more fusion happens, they can fuse heavier elements. This keeps repeating until iron accumulates or starts to build up in the core. When only iron remains, there's a problem. Iron cannot get fused. That means nuclear fusion completely stops for the last time, and the core crushes under gravity, becoming compressed, like before. Now the star's temperature increases, causing an explosion known as a supernova. Now this releases enough energy for actually these iron atoms to fuse together to form elements even heavier than iron. That's why we see elements like gold, for example, that's heavier than iron. Then this explosion will then scatter these heavy elements across the universe. Lastly, the remaining core can either collapse into a black hole or simply compress into a neutron star. This depends on the force of gravity acting on it. Now, moving into some more triple content is work done. So when energy is used to move an object with a force, we call this work done. So work depends on the force needed to move the object and the distance that we move the object. So that means we get the nice and simple formula, work done equals the force times the distance. And again, we're going to label the units. So the work done is energy. So this is measured in joules. Force, as usual, is measured in newtons. And the distance is measured in meters. Now this can link to power actually. So we know that power is energy or work done divided by time. So this means that power is also force times distance divided by time. In other words, this happens to be force times speed. Now this is actually an A-level equation that you'll use if you take physics or maths later. Now, more triple content would be springs. So this isn't assessed in any of combined science. So the triple students need to know that to change the shape of a spring, we need more than one force. This is because if you have one force, you're going to simply drag the spring along. Think about a table. You'll need to hold the spring in place. That means you need two forces acting on it. Now, when we use some forces in the spring, it can either compress or extend. When we increase the forces, the spring will compress or extend even more. Now, changing the shape is called deforming in this case, and there are two kinds, elastic and inelastic deformation. Elastic involves the spring returning to its original shape. Whereas inelastic deformation, the spring doesn't return to its original shape. Now, one other thing we need to look at with springs is the spring constant. So the extension of a spring is directly proportional to the force acting on it. In other words, we need more force to extend the spring more. So directly proportional also means if we looked at this on a graph, if the force doubles, the extension doubles. And if we drew a graph, it would be a straight line going through 0, 0. In other words as well, the spring constant is how stiff the spring is, determining how far the spring extends when a force is applied. And you get the equation F equals KE. F is the force, that K is a spring constant, and the E is the extension. Now the units are another world, and people forget this often. So the force is obvious, which is in newtons. The spring constant is in newtons per meter. And the extension is in meters. That's a common mistake that people forget. Another part of springs we need to know about is the limit of proportionality. Now, this direct proportional link between force and extension continues with a spring until they reach the limit of proportionality. That's when, if we extend the spring beyond this point, force and extension aren't directly proportional anymore. This also results in the spring inelastically deforming, so it doesn't return to its original shape or length. So if you draw, let's say, a graph, you have your force and your extension here, it would first start out as a straight line. However, past the limit of proportionality, it could, let's say, curve upwards. This point here is that limit of proportionality, so where the line stops being straight. Now next, we return to some content found in everyone's paper. So that's combined foundation, triple higher, triple foundation, and so on. Again, we're going to recap some of the stuff we learned earlier. So some units, scalars, and vectors. So we complete this table here first. So distance is measured in meters, and this is a scalar quantity. Displacement is also measured in meters, but it's a vector. So this is actually your position relative to your starting point. Velocity is measured in meters per second, and that's a vector. Speed is also measured in meters per second, and that's also a vector. And lastly, that's actually a scalar, and forces are measured in newtons and is a vector. Now, you may need to memorize a few rough speeds as well. So you need to remember the approximate speeds for some common moving objects, like someone walking, running, cycling, someone in a car. You should also remember that the speed of sound is approximately 330 meters per second. Now, as a little continuation, how do we calculate speed? So speed equals distance divided by time. Now, sometimes in the exam, you could get different units. For example, you might measure speed sometimes in, let's say, miles per hour or kilometers per hour. This is because we measure distance and time in different ways. So your unit for speed is first your unit for distance, which can be things like meters, miles, kilometers, and so on. And we divide this or have a stroke like this, divided by your unit for time. Next is acceleration. So this is simply how fast the speed or velocity of an object changes. So for example, something accelerating quickly will mean its speed increases but very quickly. Now, acceleration is usually calculated by the change in velocity, so its final one minus your initial one divided by the time. And u is your just remember which way these go round is U and V in the alphabet. So U goes before V. Now, you may have other formula involving acceleration, such as this one. And again, you'll be given all these formulas anyway in your exam on a sheet. Now, linking to some triple-only content is some space physics again with orbits. So I'm going to draw a free body diagram showing the forces acting on a satellite orbiting the Earth. So let's say in the middle we have the Earth. Remember, this isn't to scale. Let's say we have our satellite. Then it's a nice drawing there. Now I'll draw all the forces in another colour. So what we have is a force acting downwards, which is gravity. And we'll also have a thrusting force going forwards like this. Then it will end up taking this path, going around in a circle, around the Earth. Now, it could be commonly asked for some questions, such as how do these forces keep the satellite in a stable circular orbit? So the gravity acting on the satellite wants to pull it into the Earth. However, the forward force, or the thrusting force, doesn't allow it to. So it has enough speed to escape or stay above. And as a result, the satellite will end up going in a circular orbit. Now, another question could be, why does the satellite change in velocity, but not change its speed? In other words, you could also say why it accelerates. So it changes velocity because, let's say, this, if you remember, is a vector, which is your size and direction. The size stays the same. So the size or magnitude stays the same, but the direction changes. In other words, this also causes a change in velocity, which happens to be acceleration. Now, some further notes about orbits could be some special orbits, like geostationary orbits. So these are ones that orbit every 24 hours. So that means they observe the same area. So they'll stay focused on one part of the Earth, let's say one country, for example. And lastly, another note could be, why does a satellite orbiting close to an object need a faster orbiting speed? So this is actually because when closer, gravity is stronger. So it needs to be faster to escape this gravity and not get pulled in. Now, going back to some content for everyone are these distance time graphs. Everyone gets mixed up with these every year. So one graph you could be taught about or shown in an exam is a distance time graph. That's where on the y-axis we have distance, on the x-axis we have time. So we record someone's distance over time. This could be, for example, someone cycling away from a point and having their distance recorded regularly. Something like this. Now this is a simple graph, and you could be asked to calculate the gradient. But what does this gradient show? Now the gradient is your change in y divided by the change in x. Now the thing is, the y-axis represents the distance, and the x-axis represents the time. So this gradient is your speed. For example, this has a shallow gradient. This tells us the cyclist is moving away at a lower speed. Whereas this one is much steeper and is faster. You could also note that it's moving down, so back to the point, or back to the start. Whereas this flat line just shows the cyclist is not moving. so its speed is 0. Now the other graph you could be shown in the exam is the velocity time graph. So again, these are similar to the previous graphs, but show an object's velocity over time. For example, a racing car accelerating in a straight line. This could be one example. For example, we'll have this, like this. This time, what does the gradient tell us? So the gradient, as you know already, is the change in y divided by the change in x. Your y-axis goes up and down, which is your speed, and your x-axis, as usual, is time. Now speed divided by time, or a change in speed divided by time, is acceleration. Now, what is happening, let's say, when the line is rising, like this, flat, or falling, having like a negative gradient. So when the line is rising, the object is accelerating. When the line is flat, it is at a constant velocity or speed. And lastly, if it's falling, it's decelerating. And then another nice feature could also be to find the distance. Work out the area under the graph. And I'll highlight this right now. Next are some laws of motion. So this is on everyone's paper except triple foundation. So first we have the first law, Newton's first law. This is like to do with like inertia. This is like the tendency of objects moving. So if there's no force acting on an object, the objects will remain stationary if it is stationary, and it will continue moving if it's already moving at the same speed and direction, so it maintains its velocity. So this means we need a force to change the motion of an object. Now how we change the motion is in Newton's second law, acceleration. So the acceleration of an object is proportional to the resultant force acting on it. That means if we double the force, we double the acceleration. However, this depends on the mass of the object, and hence we get this familiar formula. And we'll label the units again. Newtons for the force, mass in kilograms, and acceleration in meters per second squared. Now finally is Newton's third law. This is the weird one. So when two objects interact, they exert equal and opposite forces to each other. For example, let's say we have someone in space holding a bag and they're not moving with a bag. Not moving at all. Now when they throw the bag forwards, they themselves start to move backwards. And we want to use Newton's third law to explain this. So before, Let's say this is our astronaut, and this is their bag as well. So they're like not moving. Now, when there's like a forward force acting on the bag, there is an equal and opposite force acting on the astronaut. So they go backwards. In other words, the astronaut pushes the bag forwards and the bag pushes the astronaut backwards. Now, for higher tier on both combined and triple, they'll need to know about momentum. This might come up on their exam. So this is another hard concept along with the like laws of motion, which we already looked at. So think of this as the energy of the moving object, which depends on the object's mass and velocity. We get the equation momentum equals mass times velocity. So momentum combines the two units together. So we have kilograms of mass, meters per second for velocity. And that's the unit for momentum. Now, both tiers or groups would need to know about the conservation of momentum. So as you've learned in other examples, let's say in other sciences, things like to stay the same before and after in a closed system where nothing escapes, like energy. Now this includes momentum as well. It stays the same before and after. Now here's a good note. Objects heading in an opposite direction have negative momentum. So we usually say that objects move from left to right have a positive momentum, and the ones moving from right to left have a negative momentum. Now, two different things can happen depending on the paper you're taking. If you take combined science, you only need to describe and explain situations involving this, whereas triple science will need to involve a bit of calculations with this. Now we can apply this conservation of momentum to what we looked at earlier. So someone in space is holding a bag, not moving. When they throw the bag forwards, they move backwards, but slower. So explain why this happens using ideas from the conservation of momentum. So before the astronaut is holding its bag, and they're not moving anywhere together. Now, after, total momentum is the same. So before, the total momentum, since they weren't moving anywhere, is zero. That means afterwards it must also be zero. We know that the bag will move forwards. This will have a positive momentum. whereas the astronaut will have negative momentum to balance this out. And they'll move slower backwards because they have a higher mass. Now for triple higher, let's use the same situation and put some numbers in. So sometime after the astronaut threw the bag speed was 10 times faster than the astronaut's. So let's say the astronaut weighs 75 kilograms and the bag weighs 2.5 kilograms. And we want to calculate the speed of the astronaut moving backwards. So we knew that the momentum is zero. The total momentum is zero. So what we have is our astronaut again, drawing a crappy figure for the, I don't know. It's the only one I could think of. They're moving back. And then you've got the bag moving forwards. Now this weighs 2.5 kilograms. Whereas the astronaut weighs 75 kilograms. Now let's say the astronaut moving back is moving at v meters per second. So their momentum, since it's going leftwards, is negative. So this has a momentum of minus 75 v. Whereas the bag moving forwards, it's 10 times faster. So its momentum is 25 v. Hang on, I don't think this is possible. Right, this doesn't make sense, sorry, this is a bad example, but the calculations are here. Now, another topic for triple higher is changes in momentum. So we have another formula again. So we already knew that force equals the mass times the acceleration. Now, acceleration, we already have another formula for that, which is v minus u over t. In other words, it's the final minus the initial velocity. Now, we see that mass times velocity is actually momentum. So we have the initial minus, so final minus initial momentum, so that's a change in momentum. divided by time. So this is important when it comes to safeties. So we want to use this formula to explain how safety features like crash mats, crumple zones, and so on reduce the chance of injury. So to reduce the chance of injury, we want to reduce the force of the impact. To do that, we need to make whatever this is lower. So you have the same change in momentum, however, things that are soft like crash mats and crumple zones, these extend the time taken to change the momentum, or basically slow down. So if you extend the time becomes larger. That means you're dividing by something larger. So that means the force is reduced. That means the impact is reduced and you have your reduced chance of injury. Now next is an entirely new unit, which is waves. Now, the wave types, like first section of the specification, is on all triple papers, but might be in the combined papers. So these are your wave basics. So there are two types of waves, and define and draw each type, and give at least one example. So first is your transverse waves. They look like these little sine waves from maths. We can draw a few things on here, such as the direction of energy transfer, from peak to peak. For example, is your wavelength, and this is your amplitude. Now, transverse waves will have oscillations 90 degrees to the direction of energy transfer. One example would be, which is like another section, any electromagnetic wave, such as, let's say, light. The other wave is a longitudinal wave, so these would be more like lines like this. Still, they have a direction of energy transfer, like this. However, they oscillate parallel to this. In other words, they go forwards and backwards, whereas transverse waves go side to side. A good example of a longitudinal wave is sound. Now, we've already annotated the transverse wave on the previous slide, and we'll do it again. This is your direction of travel. This is your amplitude. And your wavelength is, let's say, peak to peak. Now, what's meant by the frequency of a wave? So this frequency is how often something happens. This is actually how often a complete wave cycle is completed, or how many waves pass a certain point in a second. Now, there are a few ways you could calculate frequency of a wave. One of them could be 1 divided by its period, which is, in other words, time. How long it takes for one wave to complete a cycle. Another way you could calculate frequency is using this formula and arranging it. So you'll eventually get the frequency is your velocity divided by your wavelength. This comes important much later on when we look at electromagnetic waves. Now we're going to label each formula with a unit. Frequency is measured in hertz. The time period is measured in seconds. Now, v is your speed, or your wave speed. That's in meters per second. Your frequency is in hertz. And this here is the wavelength. That's now, one of the practicals could be reflection. So you need a reflective surface that can be, let's say, a plane mirror or a glass block. Now, this is how you're going to set it up. So let's say you have your plane mirror here. Then you'll have your normal drawn out. That's at 90 degrees here to the surface. Then what you'll have is your ray box that shoots out some light. And that should hit right here. And you'll trace this path, and don't forget to label its direction with arrows. And then it will reflect off the surface like this. And you'll often have some crosses here, 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 and that's your direction there. Now you'll measure some angles here. First of which is the normal to your incident ray, your incident or incoming ray, and that will be called this angle here, the angle of incidence, and this angle here, which is your angle of reflection from the reflected ray to the normal. Now, after you've done this measured, taken measurements and so on, you should repeat this with different surfaces. Let's say rough ones to investigate diffuse reflection, where light could just jump around anywhere, and you won't get like a nice image. Or let's say with other smooth surfaces. Now, as a bit of safety, remember to turn off the ray box when it's not in use, as they can get hot. Now, the other practical is refraction. So this is where instead we have a transparent material. So this would be things like glass, perspex, and so on. You'll have your normal, and then you'll have your incident ray coming from the ray box into the material and hitting this point here, like this. And then you'd see it go through the block like this, and you'll see where it goes out at the other end, like this. And again, where it exits the block is the normal. Now you're measuring a few different things this time. Again, your angle of incidence is the same as before. This time, when it goes through the material, it refracts. So you're measuring the angle of refraction. And remember, you'd want to repeat this for different materials and different angles as well. And again, for safety reasons, turn off the ray box when it's not in use because it gets hot easily and you don't want to burn yourself. Now, next is for mainly combined science, electromagnetic waves. So all electromagnetic waves travel at the speed of light, which is roughly 3 times 10 to the 8 meters per second. You may want to remember that. Now, thing is, many electromagnetic waves will have different properties because they have different frequencies, wavelengths, and so on. So ones with similar properties are grouped together with similar frequencies or wavelengths. Now down here we have a table. Now at the top we have the highest frequency. And you also have your shortest wavelengths. Whereas at the other ends you'll have a low frequency and your longest wavelengths. So first we start off with radio waves, and now these, by its name, are used quite often to transmit radio signals. These could also be used for, let's say, Wi-Fi, like data transfer, and so on. Now, microwaves are mainly used for satellites, and as well, cooking foods in microwave ovens. Now, infrared ones, wavelengths of light, they are often used to detect heat. They could also be used to change temperature. Visible light is quite useful to us. For example, it has many uses such as optic fiber cables. That's like your Wi-Fi as well. And just simply seeing things. Ultraviolet radiation could be used for, let's say, suntans. Hidden inks, and so on. But they do have a risk of, let's say, developing like skin cancer. Now, X-rays and gamma rays are used in medical backgrounds. It's like imaging and so on. So just remember these three have a risk of developing cancer. So this depends really on the dose. Now, I've got some further information on these electromagnetic wave properties. So first are radio waves. So these can be produced from electrical currents using alternating current. So these, like alternating currents, will also have their frequency as well when they go forwards and backwards as well. As the frequency of this alternating current and the radio wave is the same. For example, if the frequency of alternating current is, say, 50 hertz, it's found in the mains, the radio waves given out will have a frequency of 50 hertz. Radio waves can also induce an alternating electrical current, and that's like the ones you find in oscilloscopes. Now, for microwaves, some are used for communications, and some microwaves can be used for cooking because they are absorbed by water molecules. That's for some wavelengths only, and they make things hot. Now, gamma rays, those are a big link and throwback to physics paper 1. This is a form of ionizing radiation which comes from an atom and can knock electrons out, making an atom charged, an ion. This could be good, let's say, for even destroying cancer cells in high doses of gamma rays. Now, for gamma rays and X-rays, and to an extent probably UV rays as well, there are doses in sieverts, but you don't need to know this unit. And these sort of like measure the risk of being exposed to these like radiations. And this risk ultimately contributes to your risk of developing cancer as well. Now, the thing is, this risk isn't always too bad because there are sometimes benefits from, let's say, having an X-ray to look, let's say, look at your injury and get the right treatment. Now, as a link to electromagnetic waves is a bit of space physics once again for triple science students only. So this is the concept of redshift. So when astronomers in, let's say, the 1900s first observed light from space, they noticed that light from distant galaxies had longer wavelengths. They appeared more red. They also noticed more distant galaxies having a much longer redshift. They appeared more red again. Now, decades later, the same galaxies still emitted light, but seemed to have a larger redshift. This meant that the galaxies were moving away from us. In other words, the universe was expanding because no one was really moving at all. This actually acts as evidence for the Big Bang because we must have all started from a hot, dense, small sphere to expand to where we are right now. Now, as a further note, the expansion of the universe, for some reason, is accelerating. And we don't know why. This is why we still do science. Now, going back to some combined, like a science stuff, is some more definitions for waves. So what's meant when waves are, let's say, reflected, refracted, transmitted, and absorbed? So when waves are reflected, that's quite obvious. It will go in a different direction off the surface. Refracted, it will be um, it'll be entering material and will bend away or towards the normal. Waves that are transmitted means they are passed through something. For example, light can be transmitted through glass. It passes through glass. And absorbed means it's stopped, and energy is transferred to the object absorbing, and also it doesn't get reflected. Now, much larger focus is placed on refraction, where we use wavefronts to explain how this works. For example, light going in from air to glass. So let's say I have this boundary here, air on the left, glass on the right. Now, if you've been paying attention, even though you're not part of, let's say, triple science, you notice that there was a light practical where a light ray was shone into from air and then into glass. So it's best to think about this light ray that enters the glass as like a little wide wavefront. Something like this. Like a longitudinal wave almost. Now, the thing is, when like waves or let's say light will hit a more dense object, they will slow down. However, this end of the wave hits the glass first. That means the right hand side of the wave will slow down first, whereas the left side will continue on going faster. And what you get is this little bending effect here. Eventually, what you get are some waves going in a slightly different direction. So if we draw the actual direction in the middle, like this, they kind of go in this path. That's what refraction is. Now, finally, a practical for combined science, which is the infrared radiation practical. So in this practical, you will look at infrared radiation being emitted or absorbed. So if it's something is being emitted, it gets like shown outwards to something. Whereas if it's absorbed, like the energy from this infrared radiation is well absorbed. Now, there's some common equipment you need to use for each practical. To investigate infrared radiation being emitted, you'll use a Leslie cube with hot water, and they'll have this Leslie cube will have different surfaces. You'll often use a heat-proof mat, let's say, on the bottom. Some sensors like an infrared sensor. This measures temperature, as well as a ruler. Whereas for the other practical, for looking at infrared radiation being absorbed, where there are many variations, you'll have a heat source, different surfaces, and a way to measure temperature. Now that's what causes the variations. This could be anything from, let's say, Vaseline melting, causing pins to drop, or some thermometers, temperature probes, or even just the infrared sensors again. Now, the first method for the infrared radiation being emitted is this. So first we fill a Leslie cube, like almost full of hot boiling water. Then we place it on top of a heatproof mat on top of some A3 paper. Now the heatproof mat is needed so that heat doesn't like get lost to the table by conduction. Now as a note, Leslie cube has 4 different surfaces, which I'll tell you about in a bit. Now, you draw a square around the Leslie cube on the piece of like A3 paper, where each side is 10 centimeters away from one side of the Leslie cube. Now, using an infrared sensor along with the description of the side, you'll measure the amount of infrared radiation emitted, which is measured as temperature, and then record it. For example, you could be looking at the matte white side and you'll measure a temperature. And don't forget to do this like 10 on the 10 centimeter line away from the side. Then you repeat step 3, measuring the temperature on different sides, and you do this for all the Leslie cube like surfaces. And lastly, you come to the conclusion that a higher temperature recorded means more infrared radiation is emitted by the surface. Now, more infrared radiation should be emitted with black surfaces and matte surfaces. So these are like more dull ones, they're not really shiny, whereas less with white surfaces and with shiny surfaces. Now, the other method for measuring infrared radiation absorbed, I'm going to use the one with like the Vaseline, so the Vaseline melting. So first we have 2 slabs lined with the different surfaces on all sides. Let's say one with a shiny white surface and the other with a matte black surface. And they need to be both the same distance from the Bunsen burner, which is our heat source, let's say 20 centimeters. And obviously they have to be supported to stay upright. Then you add a 10-gram blob of Vaseline to each different surface type. So you'll have one blob of Vaseline on the matte black surface and one blob on the shiny white surface. And you need to place the Vaseline, the blob, on the side that's not exposed to the Bunsen burner, facing away instead. Next, you embed a drawing pin into each blob of Vaseline, and you need to make sure it's supported before you start the experiment. Now, to start the experiment, you turn the Bunsen burner on onto a blue flame and you start a stopwatch. Now, you record the time taken without stopping the stopwatch on each surface for the Vaseline to melt and cause the pin to drop. As in, let's say it takes 2 minutes for the Vaseline to melt and let the pin drop on the matte black surface, and it takes a bit longer on the shiny white surface. Now, a faster time means more IR or infrared radiation is absorbed, so it absorbs much better at a faster rate, so it causes it to increase in temperature, it causes the Vaseline to melt much faster. Now, what you expect here is that black surfaces tend to absorb infrared radiation better, as well as matte ones. This almost lines up with the emitted ones, because in fact, good absorbers of infrared radiation also emit infrared radiation well, whereas the poor absorbers, in other words, they reflect, you expect them to be white and shiny. Now, the next final unit is magnetism. So we'll start with some basics. So you're probably familiar with some bar magnets, which are a common example of a permanent magnet, as these will have different poles at each side, which are north and south. And that's the bar magnet there. Now, two magnets will attract or repel depending on the poles. So if they're like or same poles, for example, north and north, south and south, they will repel. Whereas if they're the opposite, for example, north and south, or south and north, they will attract together. Now, you need to know some examples of magnetic materials. These are iron, nickel, cobalt, and steel. Now, these materials are naturally attracted to magnetic fields and then can become magnetic themselves. These are induced magnets. Next, you need to know about magnetic fields. So, this forms the basic stuff for later things like motors. So, we need to know the diagram of a magnetic field around a bar magnet. So we'll have a bar magnet again. North at the left, south at the right. I'll highlight each end. Now, when we draw the magnetic field lines, they run from north going out to south. So they start at north and they go outwards. You don't need to necessarily show that all lines will connect back to south, but you need to show arrows and at least multiple lines like this. Now some will loop around a bit like this. And again, you need to draw your arrows. And then you'll have at the south end, this is the receiving end of all these magnetic field lines. Now, how do we know it's like this? For example, how do we know where the lines even are? So we put paper on top, over the top of the magnet, and then we sprinkle iron filings over it, and we get a very similar shape, often quite circular shape. How would you also know the direction? We use something called a plotting compass at various points around the magnet, and we record the direction and the line going through it, and that's why we get these arrows here. Now, if we could really see the magnetic field lines a lot better, we would notice that there aren't as many iron fillings or as lines further away from the magnet. This also means that the strength of the magnetic field decreases when you go further away from the magnet. Next is electromagnetism. So, as the name suggests, electricity and magnetic fields are linked together. So let's say if you have a straight wire with some current, we can use the right hand corkscrew rule to determine the magnetic field. Now to use this rule, make a thumbs up shape with your right hand. The thumb's direction is the direction of the current, while the fingers that curl around is the magnetic field. For example, draw the magnetic field for this rule. Using this rule, for example, a wire carrying current vertically upwards. If you use the rule as seen in the diagram, you would see that the magnetic field wraps around like this. Now let's say, what if the wire is horizontal coming towards you? Again, we'll use the right hand rule, and we'll see that the magnetic field wraps around, from our perspective, like this. So just remember, you need to draw multiple lines for magnetic fields. Next, we need to know about solenoids. So let's say if we shape a wire into a coil, we can see that the magnetic fields line up together. So a solenoid, or a coil, looks a bit like this, like a little spring. Let's say the current is heading in this direction. Now, when the wire goes up like this, we'll draw the magnetic field. We'll draw some dotted lines, and else we'll draw when the wire current goes down like this. We'll draw the magnetic field. So they will, using the right-hand rule, it will go like this. When it goes down, it will go inside the loop. So what we get is a very strong magnetic field going through, like as if it was a bar magnet. So to get this, we use the right-hand corkscrew rule. Or to find the magnetic field direction, we could do the opposite. So we use the same right-hand rule, but we use our curled fingers to match where the current flows and like how the current will coil round. And then you'll find the direction of the magnetic field is where your thumb is. Now, moving on to electromagnets, three factors determine how strong the magnetic field of the solenoid is. So the first is the number of turns in the coil. So if we increase the number of turns, if we have more loops, the electromagnet becomes stronger. We could also increase the strength of the electromagnet or the magnetic field by having more current in the coil. We could also put something called a core, so let's say some material inside it, like an iron nail. Because this will amplify the magnetic field and sort of direct it. So if as a core, the solenoid is actually known as an electromagnet, so it becomes a strong magnet and it can be turned on and off. This is quite useful. Now, the thing is, you'll need to know why it has to be, let's say, soft iron. It has to be soft iron, so it like let's say when it's hard to induce a magnetic field that permanently. In other words, if we didn't use soft iron and we turned on the electromagnet, when we turn the electromagnet off, there would still be a magnetic field because that iron would become an induced magnet. Now, this useful on and off property makes electromagnets useful in many ways. One example could be a school bell, like this. Now, when the switch is closed, when the switch closes, so the electromagnet turns on. Now this causes the contacts to go back. This soft iron armature gets attracted backwards. That causes this little arm to go back and strike the gong. However, when the contacts are pulled back, the circuit is broken and current can't flow. That means the electromagnets then go off, and then the contacts go back into place as well as the striker and so on. The arm will go back to where it was. And then it repeats again. It closes, the contacts close, the current can flow, the electromagnet turns on, it pulls the arm and strikes the gong again, and it repeats forever. And that's how we get the striker repeatedly striking the gong, and that causes the school bell ring. One that you hopefully won't want to hear again for a while. Now, another good use of an electromagnet is using relays. So we've got a diagram here. So this works almost very similar to like the school bell. So let's say we turn this isolated separate circuit on. We then get our magnetic fields. And that means this attracts the spoon and it'll start to turn it. This also means that the switch then closes, and that means the other circuit will turn on. That's how we can use one circuit to turn on another. Now, before we look at the final bit of today's lesson, which are motors, we need to be familiar with Fleming's left-hand rule. So you need to remember this for your exams, though you could see others making this weird shape in the exam. So remember, the middle finger is your current, your first finger is your field, and the thumb is reserved for force. And using this, how can we tell, let's say, which way the wire will move here? So to use this rule, we'll match one finger up, actually the B here, right, this V is current, right. So since I've labelled these, well, let's say match one finger up with what's on the diagram. So let's say we'll match up the fields, our first finger going from left to right. Then I'll rotate the other hand so that the other finger will line up with what else is on the diagram. For example, the current is moving from our side away from us. So if we rotate it, keeping the field, your first finger going from left to right, and then your middle finger is going away from you, you'll see that your thumb is pointing down and your force is therefore acting down. Now, hope you've memorized this because now we're going to look at motors in a bit. But first, we need more notes. The force produced is strongest when the current and magnetic field cross at 90 degrees to each other. So if they intersect or cross when they're at the diagonal, they're going to be a bit weaker. There are again a few ways to increase the force exerted on the wire. These are almost similar to the electromagnet one. So we can increase the strength or density of the magnetic field. We could increase the current in the wire. We could also increase the length of the wire. This links in with the equation on the formula sheet, F equals BIL. We could also see that the force is weaker when the wire is further away from the magnets. This is because the magnetic field is weaker when further away. And finally, this is it, the last slide, the motor effect. So I've got a model here that's similar to one of the first motors ever created. Using everything you know so far, like Fleming's left-hand rule, explain how this simple motor will rotate. And as a bonus, which way does it rotate? If you remember, current can flow through conductive materials like iron and so on. Let's say that's the magnet. So current can actually flow through the magnet. Current flows from positive to negative, so current will flow this way, which I'll draw in green. And we'll come back up here, join here, and go here. Then we'll have the magnetic field lines drawn in yellow. So they go from north to south. Like this. And we can see, especially these 2 points, that the magnetic field cuts the current at 90 degrees. And we can use Fleming's left-hand rule. So we've got the current field going this way, current going this way, going up. So on the left-hand side, it's going, force acts towards us. Whereas on the other side, it will act away from us. So that means we get a little turning motion, and that means the motor will actually rotate anti-clockwise. Because if I draw the magnetic fields here as well, and the current, so the current will go this way, and then the magnetic fields, which will go from north here to south. The force will act this way on this side, and this way on the other side, and then that means we get an anti-clockwise rotation. Now that's the end of the lesson, and good luck with your final exam. And please go through these notes again and again because these units are harsh and hard.